Okay, we're going to look at quadratics a little more closely. So we had talked about naming polynomials by their degree, and now we're going to get into quadratics, which are degree 2. So we're going to start there. A quadratic function is a polynomial of degree 2, which that means, the power, I should say the highest power of x is 2. So parabola, that's the shape or the name of the graph. We call it a U-shape. We've already seen these. It's one of our parent functions that we studied, and maybe it's good to talk about that. We're talking about the parent function here, y equals x squared, or f of x equals x squared. So now we're going to talk about some key features on that graph, on that parabola. So here's things that we're going to look out for, which I think we've already mentioned this, but we're going to now officially define it, the vertex. So the vertex on the parent is the point 0, 0. But what we can think of it as is it's a maximum or minimum point on the parabola. We can also call it a turning point. It's the turning point. Remember that a degree 2 has at most one turning point, and so the vertex is that point where it actually turns, or where the graph changes from increasing to decreasing. The axis of symmetry, so that's the vertical line of symmetry through the parabola. The parabola always has symmetry, and it's going to be always a symmetry or reflection. There's a line of reflection, so maybe I'll call it that. Maybe that's a little bit better. The vertical line of reflection. And it's always going to go vertical. When we talk about this axis of symmetry, we have to give it an equation. Vertical lines always have the equation x equals. So it's going to be x equals some number. And we'll talk about how we know what that number is a little later. Symmetrical point. So now once we have our parabola, our vertex, so like here's a look at a graph. Let's say we're looking at the parent function. There's our axis of symmetry. A symmetrical point means, like, if I have one point on the axis of symmetry here of a height of, say, 3, on the other side of the parabola will be like the sister point. That's the symmetrical point. There's all these symmetrical points. So when you start graphing points, you don't have to plug in on both sides. Once you get one on one side, you can go graph the symmetrical point. Okay, and we'll define that as the mirror image. I like sister point. I'm just going to say it's the sister point. On the other side of the graph, and it's equidistant from the reflection line, so the axis of symmetry. And behavior. We have an even degree polynomial. So from before, you should know that that means we have the same end behavior. The domain, that's going to be all the possible, remember domain is x values of the function. And the range is going to be all the possible y values of the function. So let's look at the parent function, y equals x squared. So I'm going to draw my x and y axis like this, because I know the parent function doesn't go below the x-axis. So if I want to graph the parent function, we know that we want to use points like, I'm going to start at -3, -2, -1, 0, 1, 2, 3. So we can just use those points. So if I plug -3 into the parent, I square it, I get 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. So let's graph the parent function here. So we've got 0, 0. We've got 1, 1. So I'm going to go by 2's here. So that's 1, 2, 3, 5. Okay, so we've got 1, 1 is there. 2, 4. 1, 2, 3, 4. 3, 9. 5, 6, 7, 8, 9. Now, this parabola, we know it hasn't been shifted at all. So let's look at that axis of symmetry. I'm going to draw it in white right down the... We know there's going to be the axis of symmetry always goes right through the vertex. That's the only point on the parabola that doesn't have a reflexive point. So the axis of symmetry always goes through the vertex. So now when I graph the other side, I just go equidistant over. So it was 1 unit over. Sorry, because I went by 2's. 1 unit over, so 1 unit over. This one's 2 units over. So the other sister point is the same height, but 2 units over. And then we've got 1, 2, 3 units over. 1, 2, 3 units over. So there's my reflexive points. And there is my parabola. A couple of things to look at here. Get rid of this stuff. Our axis of symmetry here in white goes right down the middle here. Hopefully you can see it. Right, so there's our axis. It's always going to pass through the vertex, and that's going to help us find its equation. The vertex on the parent function is 0, 0. So the equation of the axis of symmetry is always x equals a number. What number? It's whatever the x coordinate of the vertex is. Because when we say like a horizontal line, a little review, if I draw a horizontal line here, the equation of that line is going to be x equals whatever that x value is. In this case, 1, 2, 3, 4, 5, -5. Right? If I draw a vertical line here, that's going to have the equation x equals 3. So the axis of symmetry in this case has the equation x equals 0. The thing to note here, we're going to use this to our advantage, is the x coordinate of the vertex is always going to be the same as the number you use in the axis of symmetry. All right, so let's move on. Example 1, let's graph this function here, this parabola here, -x squared plus 4. So knowing transformations of functions, sketch the shape and determine the vertex. So we know this parent function was y equals x squared. What does the negative do? It's going to reflect, and then it's going to go up 4 because of the plus 4. So I've got 0, 0. Now it's going to be up 4, and it's going to open downward. There's our quick sketch. Okay. Complete the table of values with using x values close to the vertex. So we always want to stay near our axis of symmetry, meaning the x value of 0 there. Right, I'll do it this way, x equals 0. In this case, it's still at 0 because our graph was not shifted left or right. If I had like x minus 2 squared plus 4, then my axis of symmetry would shift right 2. So this number in here is really going to affect my axis of symmetry. So since my axis of symmetry is 0, we want to fill out this table, and we want to have 0 be the number that we stay close to when I pick my x's. So we're going to pick a couple x's on either side. So I'm going to go 1, 2, and -1, -2. We'll go 3 and -3 since we have the space. Now we know this thing's going to open downward, right? So let me do the axes in white this time. We know it opens downward. Oh, but it's shifted up 4, so I do need a little bit of room above the x-axis. Do that a little more neatly. All right, so we know that we're going to have our vertex is going to be at 0, 0, 4 because it was shifted up 4. But how do I get that from this equation? I'm going to write it above here. It was y equals -x squared plus 4. So if I plug in 0 for x, I get y equals -0 squared plus 4. Let me buy myself a little room here. So then y equals 0 squared is 0. So y equals 4. So when x is 0, y is 4. Okay, now let's do the same for, give me 1 second here. Just got to charge the Apple Pencil. It's getting low. So now let's plug in 1. So we've got y equals -1 squared plus 4. So we go y equals -1 times 1 is 1 plus 4. So y equals 3. Now next to that, I'm going to plug in -1 so you can see the difference. Parentheses are very important. So y equals -1 squared plus 4. See the setup here? I'm plugging in 1. Here I'm plugging in -1. So -1 squared is +1, but then I multiply it by the negative, so it's still -1 plus 4. So I get 4 minus 1 is 3. That's why I get sister points, because of the squaring. Whether I put in a positive or a negative, when I square it, I'm going to get the same value. I'm going to get the +1, right? And then I multiply it by the negative to turn it back into a -1. But that's why the sister points occur. Let's try plugging in 2. So I get -4 plus 4, y equals 0. So for 2, I get 0, and I know -2 will be that sister point. So I'm not even going to do the negatives if I know the axis is, if the vertex is 0. I just need to go in one direction, and I'll have my sister points. So I've got 0, 4. Let me rescale this. I want to go by 2's again. 1, 2, 3, 4. So 0, 4. And then let me scale out the rest of this. Go by 2's. So 1, 3. I go 1 up 3. Then I go 2, 0. 3 is going to be, I didn't do 3 out. Let's do 3 now. If I plug in 3, I get -5. 1, 2, 3, 1, 2, 3, 4, 5. Okay, now I know that the vertex is 0, 4, which means I know the axis of symmetry goes right through it. So now I can come up with those reflexive points on the other side. So that will show up over there. This one will be over here. And this one will be right there. And there's our graph. All right, so step 2 said complete the table of values. We did that. Determine where to graph the x-axis and y-axis based on your sketch and table of values. So we're using this sketch. That's how I decided how to set up my axes. Plot the points and describe the characteristics of the quadratic. So when we plot the points, I talked about like that the negatives on the other side of the axis of symmetry, or the other side of the vertex, are all just sister points. There's the symmetry there, so I don't really have to find those values. I know that negative 3 is going to be negative 5, just like 3 was negative 5. Now, that's because my axis of symmetry, or my vertex, is right here. So it's going to be the stuff that's symmetric around your vertex. It's not always going to be that 3 matches negative 3, 2 matches negative 2. If I shift the parabola right or left, it's going to mess that up a little bit. You have to know where your vertex is. We'll see some examples like that, and we'll talk about it then. Now they want to talk about this other stuff. So the vertex is right there. The coordinates of the vertex are 0, 4. And again, I can tell that even just because of what I know about transformations now. My equation was y equals negative x squared plus 4. So I know the vertex was at 0, 0, and the only shift is that it went up 4. The reflection doesn't change the location of the vertex. So I reflected it and then moved it up 4, so that's why I know it's 0, 4. It was 0, 0, but if I move 0, 0 up 4 units, I'll arrive at 0, 4. So I didn't even need the graph for that. Axis of symmetry is x equals, always x equals, because it's a vertical line. So x equals 0. Remember, it's always going to match whatever the x value, x coordinate is of your vertex, because your axis of symmetry, as you see right here in blue, has to go through the vertex. That's where the line of symmetry goes. So the axis of symmetry is x equals 0. I'll write it down here in blue as well. End behavior. It's going to go down on both sides. We know it's always going to do the same thing, so it's either does it go down or does it go up. How do I know that? I can tell by the graph, but how do I know from the equation? Again, knowing your transformations helps here, right? Y equals negative x squared plus 4. If you know that a parabola, what the parent looks like, when I reflect it, the negative reflects it downward now, I know that on both sides it's going down because of that negative in front. Okay, domain is all the possible x values. So if I look at my x-axis, is there ever an x value where I won't hit the graph, right? If I'm at an x value, I hit the graph. Even at a decimal in here. Every x value hits the graph. Even if I'm over here, it's going to take a long time to get down there, but it's going to hit the graph. Even if I'm over here. So from negative infinity all the way up to infinity. So all values are the domain. We could say x is all reals. We can just say all real numbers. There's a couple of different ways to say this. We're going to say just all real numbers. That means everything. The range is the y values. Now, it's not always the same. It's not always all reals. It changes. So this now looks on the y-axis. Can I hit the graph? This y value is on the graph, right? This y value is on the graph. We're looking at y values now on the graph. It's always on the graph up until 4. 4 is on the graph. If I go to 5 and I look left and I look right for a y value, it never hits the graph. So the range on this is all the y values that are less than or equal to 4. And that's really going to correspond with our shift up or down. If we shift up 4, it's going to be all y's less than 4 or all y's bigger than 4. It just depends on which way it opens. All right, so example 2, we want to graph this thing. So knowing our transformations, we can already have an idea what this looks like before we graph it exactly. So we know that this thing is been shifted right 3, down 5, and then it's going to be stretched by a factor of 2. So it's just going to be thinner than it should be. So I start at 0, 0. I go right 3, down 5, and then it's going to be kind of thin. So when we make our axes, we need room kind of above. So we want to go down 5. So maybe something like this. We need room to go down. And then we got to, like, it opens upward. So we're going to go below and then need a room above that when we shift down. We also need room more in the first quadrant. So I can push my y-axis over a little bit. That's based on what I know up here, that it's going to look something like this. Okay, so where's the vertex going to end up? We know the vertex, the shifts are where the vertex ends up. So I know it's going to go right 3, down 5. So instead of being at 0, 0, I go right 3 and down 5. Oops, it's right there. I like to put the vertex in the middle of my chart. So it's right 3 and down 5. That's my new vertex. Now I want to pick x values close to that vertex. So I'm going to go 4, 5, and 6. So I'll go negative, it's going to be 2, 1, and 0. So if this is the vertex, the symmetry points are going to go like these two are going to match, these two are going to match, and so on. So let's just do the ones that are, well, I'll go less than, so I'll plug in a 2 into this. So I've got y equals 2 times x minus 3 squared minus 5. So if I plug a 2 into that, y equals 2 times negative 1 squared minus 5. Negative 1 squared is just a positive 1, so then it's negative 3. And then I know by reflection, reflexive point, that one's also going to be negative 3. Right? Because I have my vertex. If I move 1 unit away from my vertex on the x's, I should have my reflexive points. Now 1 is going to match with 5. So if I plug in 1, I get y equals 2 times 4 minus 5. I'm getting 3. And that should be enough points for now. So I'm going to go 3, negative 5. I have it. Remember that that's going to also, my axis of symmetry is going to pass right through that thing. So there's the axis of symmetry. Now if I graph, say 2, negative 3, then I know I have the other reflexive point over there. And that's my 4, negative 3. Now if I do 1, 3, then I know I got my reflexive point over here, same distance apart. I draw the parabola, and that's how we're graphing these. The vertex is at 3, negative 5. My axis of symmetry is a horizontal line at x equals 3, because it always matches my x coordinate of my vertex, because it always passes through it. So my vertex, we said, was 3, negative 5. Axis of symmetry at x equals 3. End behavior is both sides up. The domain is always all real numbers. Oops. Because no matter where I am, if I pick this x value, I'll eventually hit the graph. It might take a little longer. Here, right, I hit the graph. This x value, I hit the graph. There's every x value I'm going to hit the graph. The range is not the same. These y values down here, a y value of negative 7 or whatever that is, right? Negative 8, it's not going to hit the graph. Negative 7, not going to hit the graph. When do we start hitting the graph? Right here at negative 5. So the range is all y's that are bigger than or equal to negative 5. So negative 5, it hits the graph. Here's like negative 1, it hits the graph. Here's like 1, I hit the graph. So that's my range, all y values bigger than negative 5. This one, I would like for you to try to do on your own.